So I'm going to be talking today about chemical gradients and polymer dynamics at the Epoxy-Amine iron oxide interphase. So this is, as Simon said, part of the SUS-Cord Prosperity Partnership with AkzoNobel. It's also part of a collaboration that I've been running with the Institute in Dresden. So I want to start out by very briefly talking about what we mean by polymeric interphase regions in this context and why that might be relevant in the context of corrosion-resistant coatings, which is obviously the focus of this conference. So when we're talking about the polymer interphase, we're talking about a region where the polymer has distinct chemical and physical properties compared to the bulk. And that happens as a result of interactions with an inorganic interface. So that might be pigments when we're thinking about paints, or the metal surface underneath. So generally in the literature for corrosion-resistant coatings, these kind of interphase regions have been linked in often quite a hand-wavy way to things like loss of adhesion, leaching and transport. I think Reza gave a really good talk on Monday that showed exactly that, how transport can happen around pigment particles, and also fracturing. So these interphase regions are often considered a weak point, but actually we don't know that much about them. They're very hard to access because they're often buried beneath a great deal of bulk coating. And so this is why we're focusing in this region. So we selected an Epoxy-Amine system to study initially. So we're looking at diglycol ether of bisphenol A type epoxy. So these aren't possibly used as much as they were, but they are very well studied and they have very predictable cure chemistry. And so that's why we've chosen these as our model system. So generally when we're looking at epoxy-amines, in a really, really general schematic here, the development of the interphase is thought to follow this kind of route. So ideally when we apply a paint or a coating, the epoxy and amine are homogeneously mixed. And then as the cure continues, again, generally through one mechanism or another, according to the literature, the amine is consumed at the interface. And what we're left with in the cured coating then is an epoxy concentration gradient. And so that gives us physical properties because there's a change in the cross-linking density, but also interaction between the polymer and the interface gives us different physical properties at the interface, but it also gives us a chemical gradient, if this is accurate. So a huge amount of literature has been focused on the consumption mechanism here at the interface, particularly for aluminium and alloys and coppers. And there's a wide body of work that considers that the oxide on your metals, or those metals, can be dissolved by the amine, making organometallic complexes. So this is the first thing we looked at with iron. So on the left here, we've got an example of these organometallic complexes crystallizing out of a coating. And so this is the type of effect we're looking for. There's also a much more sensitive paper that really caught our eye, where Morsch used eels to show that there was a slight migration of aluminium or copper into very similar epoxy-amine systems after aging. So, however, when we kind of repeated this Miser experiment for iron and the Dejiba-Tita system, we found no evidence whatsoever of ion migration into the polymer. So that doesn't mean it doesn't happen over much longer aging times, but on the timescales that we're looking at, essentially this organometallic amine consumption mechanism is irrelevant. So that leaves us with this kind of model for what might be happening at the interface. So again, we've got a homogeneous mixture, and then we get segregation of the precursors, either due to entropic reasons, so mobility and packing, or due to binding with the interface. And then we'd have excess epoxy here. The difference between this and the kind of previous mechanism and thinking is that we would expect this to be happening on really a nanoscale, possibly even a molecular scale. So in the literature, when again focusing on epoxy-amines, when we look at epoxy-amines generally, when we're looking for chemical gradients, people have used FTIR to investigate the extent of that excess epoxy. So that's kind of our marker. How much residual epoxy is there in a thin film is going to tell you what the extent of the interphase is. So that's the next thing I did is, well, initially we did just some FTIR analysis, just some in situ curing using the ATR to focus on our bonds. So we needed to work out which band corresponded to the epoxy consumption, which is this 916 band. And then we also have this band around 1105, actually that's mislabeled there, which corresponds to these secondary hydroxyl groups that are formed during the cure. So those two bands normally develop in an inverse way to each other. We've shown that for epoxyphenolics as well. But that gives us two different things to look for, which gives an indication of the cure degree. So sure enough, when we made thin films, we found, and then analysed them using ATR, we found that the amount of residual epoxy increased according to how thin the film was. But this was for films up to 100 microns thick. However, when we looked at gold, we found that we got almost exactly the same effect. And finally, when I put some parafilm on top of these thin films during the cure, a lot of that effect disappeared. So what that tells us is that amine is being lost from the air polymer interface. So I think in the paper we said that this is due to carbonation or evaporation. I actually found no evidence of either mechanism. But so, I mean, at the moment I'm thinking it's possibly due to migration to lower the surface tension at the air polymer interface. In terms of looking at the buried interface, we can then start to think about what we're actually detecting here. So this is the model that's kind of assumed when people look at FTIR thin films, that we're detecting excess epoxy at the interface, and that forms a larger amount of the coating. But of course, when we're using ATR, we're actually probing the top of the film. So you screw your sample into close contact with the internal reflection element. And in this case, really, the sampling depth is less than 500 nanometers from the interface. If we were losing amine from the top surface and it was being frozen into the structure, we might expect to not see any difference in these systems, therefore, because we'd just be looking at that air polymer interface. So what's actually happening is that, yes, amine is being lost from the top surface, but mixing during the cure means that we're getting a more homogeneous distribution of that excess epoxy in these systems. Again, in reality, I think what we're seeing is probably a mixture of these two bottom scenarios, so we get some excess at the air polymer interface. Regardless of that, this type of experiment is not useful to look at the buried interface. So we've come up with a different approach. I'm really focused on the AFM-IR technique generally. So to investigate the chemical structure near to this interface directly, we take a thick coating and section it using ultramicrotomy. And then we can look at that interface directly using AFM-IR. So Dom gave a really nice talk yesterday about AFM. The difference between ordinary AFM and AFM-IR is that we have a pulsed infrared laser focused on the sample surface. That means that if that laser is tuned to a wavelength that's absorbed by the sample, we get some thermal expansion, and you can detect that by monitoring the position of this probe that's in contact with the surface. So we can either map at one particular wave number, or we can step through the different wave numbers and get very localized infrared spectra. So that lets us look at the chemical structure close to the interface. I've also done some experiments using this nanothermal analysis technique where we heat the probe up and detect local TG values or thermal transitions. And also I'm interested in looking at oxidation at the buried interface, although I'm not really going to talk about that today. At the same time, we've got this second strand of experiments using bulk techniques to analyse the same kinds of properties in composite samples. So here we're adding iron oxide pigments into the Epoxy-Amine system to generate lots and lots of interphase, and then by analysing them with bulk analysis techniques, we can get an idea of the effect of that interphase on the properties. So it's very complementary to the direct nanoanalysis. So looking at this varied interphase between ions, so we prepared samples that were sputtered iron on acetate so that they could be microtomed with epoxy on top. And here I've got some maps that show you the map of residual epoxy in the system versus the aromatic band as kind of a control. And what we often do is generate ratio images, so that's equivalent to normalizing a spectrum. And that helps us eliminate any effects from different sample volumes below the tip or mechanical properties. So this map of residual epoxy looks essentially blank. So we don't have any extensive chemical gradients here of the extent that have previously been suggested in the literature. What I did see is enhanced signal directly over that iron. Unfortunately, I didn't feel that we could exclude any kind of artifact for these particular samples. We've also got local spectra here showing absolutely no residual epoxy up to 100 nanometers close to the surface. So from this particular experiment, we could say that there may be residual epoxy very, very localized to that iron surface, but there are no microscale or even submicroscale chemical gradients. So we did the same experiment using the composite samples. And here I've isolated some pigment agglomerations of the hematite, magnetite, and goethite pigments. And then when we get the residual epoxy ratio maps, we can see that, again, there's an enhanced signal over each one of these pigment agglomerations, which is really indicating that we do have some localized epoxy close to these surfaces. We did the bulk experiment on these pigment samples, so we can look at the residual epoxy as a function of PVC. You can see that there's up to the critical pigment volume concentration, which is here 4. You can see there's an increase in the residual epoxy. And when we look at the secondary hydroxyl band, we can see there's a decrease in that for all 3 pigments. So that's really confirming that we're getting increasing amounts of residual epoxy in the system as we increase the amount of interphase in the system. So looking at that decreasing amount of cross-linking, essentially, we might expect that the TG in the interface would also be lower. When I came to look at the DSC of the composites, we found there's absolutely no effect versus PVC below the critical pigment volume concentration, except in the case of goethite, where we saw the TG actually increase as a function of PVC. When we looked at nanothermal analysis of the section, this really just confirms what the AFM-IR already told us, which is that there's no change in cross-linking density, there's no change in the chemical gradient, there's no change in the local TG as we move microns away from the surface. So the resolution of this technique is much lower than AFM-IR. So we're really just looking at sort of at most 200 nanometer kind of regions at a time. So in order to try and make sense of that we get very similar chemical gradients in the case of all 3 iron oxides, and yet we see an increase in TG only in the case of goethite, I wrote my colleague Charlie Wand into doing some molecular dynamic simulations of the surface interactions for these molecules. So here for these simulations, we're using this molecule here, MDEA, as a model for a cross-link junction in the Epoxy-Amine network. So Charlie looked at binding to these 3, these are the most thermodynamically stable interfaces of hematite, magnetite, and goethite. And when we look at the binding energies, we can see they're actually very different for, well, particularly theta, which is what we think is segregating towards those interfaces. And in the case of Goethite, you can see that it's actually very similar between Goethite and Tajiba. There's no reason to expect from these figures that we would see similar effects for all three iron oxides. So that kind of led us to a conclusion where we think that the chemical interphase is occurring as a result of entropic segregation, which just means that the amines are more mobile and they possibly pack better at that interface. It still left us with a puzzle when we look at the binding energy of the tertiary amine versus these different surfaces. Still left us with a puzzle as why on earth we'd get increased TG for Goethite when actually the binding energy appeared to be a lot lower and less favourable than it should be on hematite. So to try and understand that, we need to dig a little bit deeper into the results here. So generally, binding was happening through your through electrostatic interactions between the most kind of acidic heteroatoms in these systems, so primary amines, oxygens in the hydroxyls here, or the epoxy oxygens. And what you can see, so here the pink lines are all hematite. You can see that the gap between the surface and that heteroatom is minimal, and they don't move around much during the simulation. So that really indicates you've got strong binding. For magnetite, because there's, the oxide really shields the positive iron ions from these heteroatoms, we have even a repulsive type interaction. They move around all over the surface. And then for Goethite, we've got the, so if we take theta as an example, we've got the primary amine seeming to bond really closely to the surface, and then the secondary amine, which is represented by a dashed line here, much further away. And the same for NDEA, we have the hydroxyl oxygen bound really tightly and closely to the surface, but then the tertiary amine nitrogen is much further away. And that really indicates we've got these kinds of bridging formations, which should be very, very unfavourable. So this simulation is happening in a vacuum, so protruding out into the vacuum is never energetically great. And we've got more evidence for that when we look at the movement of these heteroatoms across the surface. So the driving force for these molecules to adopt this kind of configuration, you can kind of spot here. There's a well on the surface of Goethite, which you can see the oxygen can sit in. And that also allows hydrogen bonding to the hydroxyl group at the surface. So what happens is we think that binding is so favourable that it drives the molecule to sit in this unfavourable bridging conformation. And that actually that's happening with the polymer as well. So this same driving force is pushing the polymer to adopt certain configurations, limiting molecular mobility, segmental mobility, and giving us that increased TG as a function of the pigment volume concentration. So that's the end of my talk. So the conclusions here are, first of all, that we have AFM-IR analysis provided direct evidence that these chemically distinct interphase regions are very, very small in comparison to what's widely been quoted in the literature. And so they're less than 50 nanometers. We can't really resolve them with the AFM-IR. We can just detect that they're there. In the case of this particular polymer system, so we're now extending this work to other systems, segregation, entropic segregation of the amine seems to be the driving force for that chemical gradient at the interface. So we would expect to see a similar chemical gradient for this system with almost any, unless it was directly reacting, but almost any fairly neutral surface. For the cured network polymer, the strength of interfacial bonds dictates segmental motion in the interface. So that's a very separate effect. And we've identified, we think, these very site-specific electrostatic binding interactions that are very strong on the surface of Goethite. I'd like to acknowledge all of my collaborators at various institutes, and I'm happy to take any questions.
Any questions for Suzanne?
Well, why do you think that other people have measured such a larger gradient in these materials? Why do you think they've, why have they got it wrong?
I don't know that they've got it wrong necessarily. I think if you're looking at FTIR results on thin films, then also you may well be able to detect an excess of epoxy. That doesn't mean that that whole thickness is the interphase. It just means that you're able to detect the interphase as well as the rest of the film, I think. So I think that's probably the reason why there's not really been there isn't another direct way of measuring, like looking at functional groups, and there hasn't been before.
Any further questions?
So we have the 50 nanometer-ish resolution. Can you go better than that using a machine that might actually now work properly?
Yeah, so we have got the new AFM in the AFM-IR in the NGI now, so we can use it has better lasers. We can use tapping mode on that system, and in theory that goes down to about 10 nanometers resolution at least.
And do you think it's worth trying that, or is this?
It is worth trying that if it's working now and we have access again. That particular machine's been quite glitchy in the past, but yeah, it's something that we're definitely looking into.
Thank you.
Suzanne, I have one. The critical volumes you were showing were very low, 4%.
Yeah.
These particles are the sort of aspect ratio and size of the fibers.
The size of the pigment particles is a couple of hundred nanometers for the critical dimensions. So either the magnetite and the hematite are quite round. Goethite is a long, thin, shape generally.
So you must have very huge surface areas. I mean.
Yeah, reasonably. So I tried to calculate those, but obviously the pigments are in irregular shape, so I can't accurately. No. But if we imagine that they are smooth and perfectly spherical, from the SEM images we can get the equivalent thicknesses would be kind of below 2 microns. So in reality, though, the equivalent film thickness would be much, much lower in those systems. Does that make sense?
No, I was just sort of thinking probably tangentially that, I mean, with so much surface area, have you just got more area than you could really deplete materials to? Is there so much surface area in some of these systems, at least in the bulk, that you wouldn't, there's not enough material to deplete it, if you see what I mean. It would look like it wasn't depleted because, and that's not the case when you're looking at the flat substrates, obviously.
Yeah.
When you talk about the pigments, certainly those pigments, the area is so huge that actually only a small. So
you're saying it might be that rather than pigment volume concentration, rather than it being the.
Well, the surface area may be the more important contributor there than purely pigment volume concentration.
Yeah. No, I mean I've assigned that critical pigment volume concentration just on the basis that at this value every measurement seems to go like I lose all trends. So but whether that's actually a critical pigment area concentration, it could well be.
Okay, thank you, Suzanne.
Just one quickie really is it occurred to me is XPS or TOF SIMS a way to look at any molecular speciation at that interface?
Possibly those experiments, they are done to some extent. It's very difficult because as soon as you start making samples at that length scale that are suitable for say XPS, you're having to make very, very thin samples, which are.
I was thinking more taking the individual components of the polymer and absorbing them onto the surface.
Okay, of the pigments.
Of a pigment or a 110 hematite surface or something like that.
Possibly. I don't think you would see much in the way of chemical shifts because I don't think we're seeing much interaction. So I think some similar work has previously been done in Brussels, trying to see if there's an actual detectable chemical shift there, and I don't believe there is. If we were looking at something like esters, something where there's an actual almost reaction or something close to a covalent bond, then you would. But that's only instinctively. I haven't obviously done that.
So that'd be different to a polyester system and an epoxy system.